Okay, we're ready. Okay, today's going to be the last lecture on advanced constitutive models. And I'm going to cover a lot of material. There'll be some slides that I'm going to skip over, so don't panic. I want to keep the logic clear, though. So I'm going to try to show you how this all fits together and how we can bring together what we've been studying all semester into a logic for these constitutive models. So this course has focused on constitutive models. Now these are these equations for stress as a tensor, as a function of velocity field. And we've seen sometimes we write the velocity field in terms of the shear rate tensor, sometimes in terms of some sort of a strain tensor. And just this last week, we've seen other strain tensors, the Cauchy tensor, the finger tensor. The other things that can be in this function are invariants. So we can have the invariance of gamma dot 1, 2, and 3. Or the invariance of any of these other things. So for instance, the invariant of V would be the magnitude of V. Or we could have invariance of these strain tensors that we've talked about. So for instance, invariance of the, infinitesimal strain tensor, the finger tensor, etc. So these are the things that are all part of the kinematics of the flow. Kine means motion, okay? So this is related to the motion. So we're relating stress and motion. That's what constitutive modeling is. So we have thus far studied a number of constitutive models. We've studied the Newtonian model. We've studied any number of generalized Newtonian models. So these are of the form that I've been talking about. Stress is given by some function of the kinematics. And in the generalized Newtonian fluid model, one of the invariants of the gamma dot tensor shows up. We also talked about the Maxwell model, which was our first differential equation model. So that one is tau plus lambda d tau dt equals minus eta naught gamma dot. So this was the Maxwell model. Or we could write the Maxwell model explicitly. Tau equals minus the integral from minus infinity to t of eta naught over lambda, e to the minus t prime over lambda, gamma dot of t prime dt prime. So these are the same model. Then we generalized this one to be the generalized Maxwell model, which is very similar but has a summation of relaxation times. I won't write that one out. And then we talked about the generalized linear viscoelastic model, which is this model completely generalized with a unspecified function in front of the gamma dot. So these models have been what we've been discussing, and all along we've been trying to match more variety of rheological behavior. Okay, so as we go up in increasing complexity, we can match a wider variety of behavior. Now, last time we started working on these latter models, improving the strain measure. Okay, so recently we have sought to improve the models by improving the strain measure. And the strain measure that we had before was the infinitesimal strain tensor. And yesterday we introduced two more, the Cauchy tensor and the finger tensor. Now, when we develop these new strain measures, we're still working on a fairly ad hoc basis. And so what we found was that there were some improvements that we liked that came out of these improvements of the strain tensor. And what we did was we have to evaluate the models to see what they predict when we use these strain measures. And that's how we decide whether we've done a good thing. So for instance, when we use the minus the finger tensor in the Maxwell model, so beginning with the Maxwell model, gamma becomes minus the finger tensor, we got the Lodge model. So that one was tau equals minus the integral from minus infinity to t of eta naught over lambda e to the minus t prime. So we're saving all this exponential business, which came into our model so that we could describe time dependence. And then we're going to change the actually, I'm writing the wrong thing here. I need to write the strain version. So let me start over here. This one for the strain version is plus the integral from minus infinity to t, eta naught over lambda squared, e to the minus t prime, and then the finger tensor. Okay, not too far off. And then, as always, so I'll emphasize that, as always, we evaluate what we have done by what it predicts. So we originally evaluated the finger tensor in a Hooke's law for a solid, and as we see from this slide, we got very good agreement. Okay, so this was for a Hooke's law using the finger tensor. And then when we did this substitution into a Maxwell model, we got the result that I just wrote down right here, the Lodge model, and these predictions. So as I pointed out yesterday, there's a breakthrough in making this substitution because we finally predict a very important nonlinear property, the first normal stress coefficient. And we also predict an interesting extensional viscosity, one that's not just a constant with all manner of deformation rate. There's no x-axis listed here. That's my error. This should be gamma dot or epsilon dot. Okay? But it shows something interesting and, in fact, not a little bit reminiscent of some kinds of the data that we see. And we saw that by making this change to the finger tensor, we could eliminate the objection of frame invariance. So going through this summary, we've made a lot of progress. We've gone from constant viscosity, nonlinear viscosity, time-dependent effects, and now nonlinear effects. Okay? And we've solved some big problems. The frame invariance problem is solved. We haven't talked about that in detail, but it was solved by taking into account the improper use of a tracking mechanism for strain. We needed a tracking mechanism that was independent of rotation, and we solved the frame invariance problem. Okay, so where does that leave us now? That's where I want to take off today. What do we do now to improve? And there are actually there are two approaches. Let's say three approaches. And the first one is perhaps the most obvious. One, we can try other strain measures. So we've tried finger, we can try Cauchy, we can try others. Inside this approach, there's also a sub-approach, which is to try other time derivatives. And I talked about this at the very end of class last time. I want to do a better job of that today. So I'll talk about that a little bit next. So we can try other strain measures or other time derivatives. We can change the format of the equation. And third, we can go to molecular modeling. And those are the things I'm going to talk about today. Now, first, let me go to this issue of trying other time derivatives, starting with the equations we've got so far. So we kind of like this form of a constitutive equation. In this form, the stress tensor appears on the left, and all the kinematics appear on the right. And so it becomes a little bit more straightforward as to how to evaluate stress. We need to just put the, if we're evaluating a material function, we put the kinematics in here, or if we're dealing with a strain measure, we put it in the strain tensor. This is a function of the constitutive equation that's given to you, and then the stress comes out on the left. But as we saw with the Maxwell model, sometimes there's something intuitive about a differential equation that helps us to guess what the form of this equation might be. And this, the connection of the Maxwell model to that physical picture of a spring and dashpot in series is very compelling to a lot of people. So this equation, this mechanical analog is much easier to understand in terms of differential equations. And so the other approach besides fixing up strain measures has been to fix up differential equations. So we can turn our let's say our finger strain tensor back into a differential equation by noting how we got it into an integral equation in the first place. We started with this differential equation and we solved it to get this explicit equation in stress. We could go backwards by taking this explicit equation in stress and take the time derivative. and manipulate it algebraically a bit, and we'd get back to this original equation. Okay? So for instance, we take the time derivative of the left-hand side, we take the time derivative of the right-hand side. This has two terms in it, so you have to do the product rule. You have to do Leibniz rule to bring the derivative inside. When you do the product rule, one term shows up that has something to do with stress, and one term shows up that has something to do with rate. It's a little bit complicated. We're not going to go through it, but you can go backwards from here to here. Likewise, you can start with the Lodge model and do the same thing. Take the time derivative of this equation, partial with respect to t, okay? And then the partial of this right-hand side. Again, when you take the partial derivative of an integral, you use Leibniz rule to bring the partial derivative inside. Then you have this product here. This is a function of time. This is a function of time. So you need to do a product rule. And this is discussed in the text if you're interested in the details. And you have to manipulate a little bit to get a differential equation. Now, at the end of that manipulation, you get an equation that looks like this. You get an equation that looks very much like the Maxwell equation. Tau plus lambda times a very big set of terms, actually, equals minus eta naught gamma dot. So it looks just like the Maxwell model, except that there's an enormous set of terms here. This is the substantial derivative of the stress, which has the partial derivative in it. And then these interesting terms, del V transpose dot stress minus stress dot del V, where d tau dt is equal to the partial derivative plus v dot del tau. You may remember this substantial derivative notation from the Navier-Stokes equation. So this is the differential equation that corresponds to the Lodge model. And it introduces the idea of the time derivative, the special time derivative. Because recall that we have the Maxwell model, which is just tau plus lambda partial tau with respect to t equals minus eta naught gamma dot. So they're exactly the same, except for this has just a simple partial derivative with respect to time, and this has this mess. This mess is called the upper convected derivative. Time derivative. And it has its own history. In fact, its history is not usually related to the way I just introduced it to you as something that came out of the finger tensor. Instead, it's a kind of a time derivative that comes out of continuum mechanics, where scientists who were exploring these kinds of problems were looking at the effect of this time derivative term on the rheology that's predicted by these kind of models. We got this time derivative term in a very ad hoc way. We said, we like this physical analog. We can write a differential equation for the motion of this analog. And if we cross our fingers and don't think about it too much, we can get a constitutive equation that looks like that differential equation. But there was something wrong with doing that. And this was proven by some mathematicians about 50 years ago, that writing this term in the Maxwell model is the source of the frame invariance in the Maxwell model itself, which we then saw showed up in the generalized linear viscoelastic model. So there's some high-tech math there, but the frame invariance, the problem of stepping off the turntable, is also embedded in taking track of time changes in this way. So how do you properly take account time changes? And there's a lot of different ways. Just like there are a lot of different ways of writing a strain measure, there are a lot of different ways of properly taking a time derivative in a continuum, in a flowing fluid. And that's why we're going to end up with a list of time derivatives that are appropriate, but that all give different predictions. Okay? So the upper convected time derivative, the one that came out of the finger tensor, is one that's related to a different way of keeping track of fluid motion. We've been thinking of keeping track of fluid motion by, let's say, sitting here on the floor and watching particles flow by. You can avoid, this leads to frame invariance because of this stepping on and off of the turntable business. But if instead of sitting on the floor, if you sit on the particles themselves and follow them along, the math becomes more complicated, but you don't end up violating any laws of physics that have to do with the time derivatives that you take as you follow the particles along. Okay, so without going too deeply into that, the exact way that you decide to follow particles along can give different time derivatives that are all appropriate for replacing this incorrect time derivative in the Maxwell model. One of them is the one that we've discussed already, called the upper convected time derivative. This is actually related to the deformation of a coordinate system that moves along, moves and deforms with the fluid particles. You can use a related coordinate system that is orthogonal to the upper convected, and it's called the lower convected time derivative. Look at the differences. There's a sign change here and a sign change here, and difference between del V or del V transpose, etc. And this is another replacement for the time derivative. It gives different predictions. And then here's a third. This one's called the co-rotational. This is related to a coordinate system that's rotating at the local angular velocity. So just by looking into these different mathematical expressions for time derivative, we can automatically generate new constitutive models by just replacing this time derivative with one of these here. So now we've got these two methods for generating new constitutive equations. We start with the Lodge model. We start with the Maxwell model, and we use the finger tensor. That gives us the Lodge model. We start with the Maxwell model and replace the strain measure with the Cauchy tensor, and we get something I call the Cauchy-Maxwell model. And if we take the generalized linear viscoelastic model and replace the infinitesimal strain tensor, we get what's called the Lodge rubber-like liquid model. If we take the time derivative and replace it with the upper convected time derivative, we get the upper convected Maxwell model. If we replace it with any of the others that were on the previous slide, we get the lower convected Maxwell model or the co-rotational Maxwell model. I have these summarized in the book, and some of the characteristics of these different constitutive equations are also described in the book. So let me show you this table. First of all, as we know from the derivation I gave, the finger tensor is tied to the upper convected derivative, and it turns out that the Cauchy tensor is convected to the lower convected derivative. So when we substitute the Cauchy tensor in or this time derivative in, we get the same constitutive equation, one written in integral form, one written in differential form. This co-rotational derivative doesn't have an equivalent strain measure that's known, and here's one that we haven't discussed, but it comes out of a different molecular picture, but it's just to show you that there are other time derivatives and other strain measures that can be developed to give different constitutive equations. So I'm sure this is getting a little bit overwhelming because we started off with a relatively short list of constitutive equations, and in one day we've got a lot. And that's the story. That's the way it is. Here's another table from the book. There are a lot of different constitutive equations, and the only way to choose among them is by what they predict. So this table shows the ones we're familiar with, the generalized Newtonian model, and some advantages and disadvantages of that model. The Maxwell model, which is frame or variant, it has that partial derivative in it, and its pros and cons. The generalized linear viscoelastic model, the upper convective Maxwell model, which is the same, as it says here, same as the Lodge model. The lower convective Maxwell model and the Cauchy-Maxwell model, which are the same as well. And here are some summaries of how they behave. As we discussed yesterday, they show first normal stress. They overpredict second normal stress differences. So how to pick among them? The only way to pick among them is to know what they predict and compare that to how data actually behave. See what they predict, compare to real data. Now, actually, we haven't even begun very much with the diversity of constitutive models we could talk about now, because everything that we've talked about now has been somehow based on the Maxwell model. And that's not the end of the story either. There are other places to start besides the Maxwell model. So going to this slide, we can move forward with more development. Here's the Maxwell model in its two forms. Okay? There's nothing to say that this is the only starting point. So for instance, we could start with a slightly more complicated model. Here's the Maxwell model again, turned into the upper convective Maxwell model. Here's a different model that, if you look at it closely, looks a little bit like the Maxwell model. Here's the same term, here's the same term, and here's the same term. But we've added a time derivative of the rate of deformation term. This differential equation has a mechanical analog, and here it is. It comes from what's called the Jeffreys model. So instead of having a spring and dashpot in series, it has a spring and dashpot in parallel that is itself as a unit in series with another dashpot. If you do the prediction of how this extension relates to the force, you get a differential equation that looks like this. And we can turn it into a valid constitutive equation by changing these not allowed time derivatives into allowed ones. And we've got at least three. We've got upper convective, lower convective, and co-rotational. This is a model that people use. This is called, as a source, it's the upper convective Jeffreys model, but it's most often called the Oldroyd B model. And it has some interesting predictions. Now, you might think, okay, well, I see an infinite number of varieties now, because I could make an infinite variety of pictures like this, and that will give an infinite number of equations like this, and so now I've got a whole bunch of work to do for the rest of my life predicting what those constitutive equations do. The problem is that making more and more complex models of this type is not very helpful, because it turns out that the Jeffreys model is one subclass of our old friend, the generalized linear viscoelastic model. So this generalized linear viscoelastic model that we've talked about quite a bit has this function g in it. And this function can be anything. It turns out that if you solve this equation, this differential equation, the new one, for stress, stress is in two places, so we have to solve again, you get stress on the left, an integral on the right, and a gamma dot. Everything that's not the gamma dot you could call g of t minus t prime, and you're back to the generalized linear viscoelastic model. So, as it turns out, linear modifications of the Maxwell model, motivated by springs and dashpots, will change what you predict for g of t minus t prime, but will not change the constitutive equation. So this shut down a generation's worth of research, that realization. Going back to our Maxwell equation, though, this modification was a linear modification, adding this term on, but we can do nonlinear modifications. Here's an example that maybe actually occurred to you. Here's the upper convected Maxwell model. Normally, the upper convected Maxwell model has a viscosity here and here. What if we just put in a shear rate dependent viscosity there? Okay? That's possible, and that's called the White-Metzner model. This model will predict shear thinning, but it has some other difficulties. For instance, it doesn't predict a reasonable linear viscoelastic regime. Professor Oldroyd in the UK said, well, let's be systematic about this. If we're going to add nonlinearities to the Maxwell model, let's add all the possible nonlinearities that are just quadratic in rate or stress, quadratic in rate and at most single power in rate times stress. So here's a term with rate times stress. Here's the trace of the stress. And these terms may not look familiar to you, but if you use the advanced techniques of Oldroyd in tensor calculus, you can show that this complicated, very complicated equation takes care of all of those linear or at most quadratic terms in shear rate. Okay? So I actually can't reproduce the math of Oldroyd on this. I take his word on it. But it becomes this very big equation. And he's saying, well, if we should always walk before we run. Let's add the next level of complexity and see what we get out of them. And what you get out is a very big and unfortunately very difficult model. But it is one that at least contains a bunch of other models inside as things to compare with. So for instance, if you keep, there's the first two terms of the upper convected Maxwell model, there's the right-hand term. So with certain values of the parameters, lambda, mu2, nu2, etc., you can get back the upper convected Maxwell model. You can also find the upper convected Jeffreys model in there. And there's one that's been used called the 4-constant Oldroyd model that's in there as well. Okay? Contains all terms linear in stress tensor and at most quadratic in rate of deformation tensor. And he imposes the condition of frame invariance. Now, Giesecke said, well, linear in stress, how about quadratic in stress? So here's the Maxwell model again, these two terms and this one. And he added a term quadratic in stress. Where do I have it? Yeah. The only way, as I said, to choose among these models is to do a thorough prediction of what they predict in various flows. And that was done by a lot of researchers over the year and has been summarized by Ron Larson in his 1987 book, maybe, Constitutive Equations for Polymer Melts. Okay? If you ever get an occasion to look at this book, what's interesting about it is it really shows you how difficult this problem is, because every one of these changes, they really change a lot of different things at the same time. So you can't just, as we saw when we went through our models, when we changed from Newtonian to generalized Newtonian fluid to Maxwell to generalized linear viscoelastic, improvements that we got, for instance, with the generalized Newtonian fluid, we lost again when we moved forward. And that's actually true of these more complex models as well. So it's a kind of a frustrating business. Now, these improvements were all improvements to the differential model. You can also make improvements to the integral models, and these are two general forms of improvements to the integral models. So here's one. Again, when you look at an equation like this, try to simplify it. These are, again, stress on the left, the integral. Here's that same memory function. And then here's where we usually would see the strain tensor, and then the time integral. And this is a case of saying, well, we like the finger tensor because it gives the first normal stress difference correctly. We like the Cauchy tensor because it gives the second normal stress, but it's too big. So why don't we weight them by some function of invariance to get a little bit of second normal stress, a little bit of first normal stress, and make it ideal? And that would be the Rivlin-Sawyer's model. It has pros and cons. And a similar way of combining the Cauchy tensor and the finger tensor, but somewhat different based on a potential function u, is called the KBKZ model, which is a model that's widely used. All right, so we're overwhelmed. Here's a summary of where we are. We've fixed all the obvious flaws, and now we have too many choices. Okay? We could make predictions and compare with experimental data. Some of the models, for instance, the Rivlin and Sawyer, have undefined functions that we'd have to figure out. It's a little bit too much. It's really a little bit too much, because there are so many degrees of freedom in the problem. We've learned a lot, but it has not led down into a chute of just one equation that we're happy with, that we now understand. It's a turning point in the field of rheology. So what do we do now? And the answer is we have to turn away from this constitutive modeling and look at, instead, actual molecular modeling. So I only have 10 or 12 minutes left, and I want to give you a flavor of molecular modeling. And in fact, if you go to the Society of Rheology meeting, which is held every October, you will see a lot of molecular modeling. And that's because this is the direction the field has turned. It's turned this way because of what we just summarized, that the continuum approach hasn't led to a dead end. It's led to too much, an embarrassment of riches. We can't just sit there and play with the math. We need some guidance. It would be like, throwing darts randomly at a wall. We have to instead look at, where do we have information? In chemical engineering, when we're solving problems, we often start with an overwhelmingly complex problem, but you can often do something about it by looking at where the information starts. Where do I know something about this system? So when I start talking about polymers or emulsions or suspensions, I do know something about those systems. So for instance, for polymers, I know that they're very, very long molecules, and that in general they have an elasticity that's due to their statistical nature. So what would happen if we approached our rheology starting from that point and tried to move backwards? I think students are clever that way in derivations. If you know the starting point and you know the ending point, you can sometimes work the starting point forward. You can sometimes work the ending point backward. And so that's what we're doing now. We started with the continuum mechanics and we moved forward, but now we're going to start with the molecular picture and move backward and see what we can get. And I'm not going to be able to go into the details, just the big picture. This is the general idea of how these things are done. Okay, imagine we have a polymer that is a very, very long, squiggly mess of polymer. We can describe this statistically. Polymers are usually modeled as random walks. So if I started at one end and then took off a step in a random direction, I could make a random walk in three-dimensional space, and that would essentially model what a polymer is. Now, once we're using statistics, we can use the tools of statistics to derive this, to derive mathematics that's related to this model. And so we talk about the end-to-end distance of the polymer chain and the force that it takes to change that end-to-end vector. Okay? So a polymer chain adopts the most random configuration at equilibrium. When deformed, that chain likes to go back to that random configuration, and that's like a spring-like restoring force. So we have this picture of a random chain, but it actually behaves just like a single spring. The force that it takes to move a single spring is something we know a little bit about from physics, and so we can relate it to hopefully some stress. All right, the statistics of a random walk is that it gives a Gaussian probability distribution of the end-to-end vector. And there's an entropy calculation we can make, entropy being the tendency to disorder. And so because this random walk tends to want to be as disordered as it can be, it provides that spring-like restoring force. So from the statistics, you can relate the force of changing the end-to-end vector of that chain to the length of the end-to-end vector. We can relate the molecular force generated by a deforming chain to an integral over a piece of space that has these chains in them. So if we have a block of space and we have chains in there, we're trying now to relate this to the continuum mechanics. We're going to use statistics. So if we pick a surface and then integrate over the volume, we can get the final force, that the local stress, the local force on a particular plane, and we can relate that back to a stress tensor. Okay? In fact, we started way back at the beginning of this course talking about force on a plane of unit normal n and of area dA. And we said all of our ignorance was going to be in this stress tensor. So if we can write the molecular tension force on an arbitrary surface, we should be able to derive a stress tensor. So we make a statistical argument to get this force on a chain. And we have to consider the volume in space, and I'm not going through the details. But we can, in fact, relate the force on a given surface in a fluid full of these random walk chains to now the first moment of this paired function here. This is called the second moment of this probability distribution function psi. Okay, so again, I'm not explaining all the details, but the statistics leads to this calculation, and there are some details in the book, again, if you're interested. So this statistical approach to molecular forces gives us this expression for F. It has to do with the probability distribution of molecules. But when we compare this equation to the equation way back from the beginning of the course that relates force on a surface to the stress tensor, we've got n dot something, we can then therefore deduce the stress tensor. So this stress tensor is not a constitutive equation because it relates this second moment of the end-to-end vector distribution. So that's still a statistical quantity. So we have to bring flow into the picture. And we bring flow into the picture with another model, which is looking at how such a chain would deform in flow. And we can do this two ways. The easier way is to consider, first of all, an elastic solid. All right, so first we had to consider statistics related to a random walk chain, and now we have to consider how end-to-end vectors of a polymer chain might be deformed by flow. And this requires, again, physical modeling, and we're only going to be able to just briefly indicate to you what they are. But imagine you have a cross-linked solid. I've highlighted the cross-link points by these red dots. And I can model each of these individual chains between cross-link points as polymer chains, random polymer chains that we've already discussed. So I can reduce each of these polymer chains just to this end-to-end vector. So this version of the elastic solid just talks about end-to-end vectors. And if I just collect all these end-to-end vectors into a space that just relates the components of the end-to-end vector, I can get a distribution of end-to-end vectors. ETE is end-to-end vector. Now I need an idea in my head of how this distribution changes with flow. And the simplest is to say what's called the affine motion assumption, which is that if I deform a box macroscopically, at every length scale down into the material, everything's deforming the same way. So if I double the length of a sample, if I zoom in on the polymers, I'm also doubling the length of every vector down there. We can then perform our analysis on that model using the inverse deformation gradient tensor. So you see, in order to understand molecular models, we need the same tools that we used for the continuum models. We want to relate the initial state and the final state. There's details here I'm skipping. But at the end of the day, here's our expression for the stress tensor in terms of the end-to-end vector. We've got an expression now for the R. If we make some assumptions about the probability distribution, we can do this integral, and we can get a constitutive equation. I'm skipping. So at the end of the day, here is the constitutive equation for an elastic solid that comes out of that molecular picture. And it's the same one we've already discussed. It's the Hooke's law with the finger tensor. So isn't that fascinating? We started from a totally different direction. We started by saying, oh, we want to define strain. Let's invent the inverse deformation gradient tensor. Let's eliminate rotation, get a new strain measure. We came up with the finger and the Cauchy tensors, and then we were stuck. Here we've started again, instead of from the beginning of the problem, we've started from the end and gone backwards rapidly, and we've gotten to the same equation. So we haven't wasted our time. We've really just given ourselves a good basis in the math, and now we know, however, some molecular things to say about the finger tensor. Before, all we could say about the finger tensor was that it was one of any number of strain tensors that we might use. Now we can say that the finger tensor is associated with affine motion and end-to-end vectors on random walks. In addition, instead of having an arbitrary G out front, we have a relationship that gives a relationship between the concentration of polymer chains, Boltzmann's constant, and temperature that we can then check in our experiments. For polymer melts, we can come up with a molecular model that says that we have all these polymer chains that are entangled. If we strain them, they'll eventually unentangle, they'll eventually forget what neighbors they had. And that can be modeled by a probability jump. These are the pictures that were used by Green and Tobolsky in the 60s, I believe. Assume that you have new junction points per unit volume. Assume that the end-to-end vectors have finite lifetimes, meaning they die. So a chain lets go after a certain period of time. When old ones die, new ones are born, and new ones adopt the random configuration. And then presto changeo, I'm not going through the math, but there's some probability arguments we would have to make. But at the end of the day, we get this constitutive equation, which is the Lodge model. So once again, starting from the back of the problem and going to the front, we're getting a picture of the meaning of the Lodge model. The Lodge model comes from the idea of a temporary network. Now, before we get too excited about that, it turns out, I'll skip a few other things, that for polymer solutions, if we model polymers as an elastic spring with some drag on the ends, these balls on the spring, and we do the statistics on those, we get the Lodge model again. We get the upper convected Maxwell model. So the end of the story on molecular models is that although they're terrific because they give us some insight into how the molecules actually behave and why the equations turn out the way they do, you can start from vastly different molecular models and get the same constitutive equation. The temporary network model and the dumbbell model both give the upper convected Maxwell model or the Lodge model. Okay? So we still sort of have an infinity problem. There are a lot of different models we could pick, but we've got some parameters around them that specify requirements that have to be held on those equations. And the molecular modeling approach is giving us the advantage of giving us some insight as to what the various parameters in these models actually mean. Okay, so that'll be that. On Friday, I'm going to start talking about rheometry, the measurement of rheological properties. And we have a homework due tomorrow.